Welcome to lecture number 2, cost function and lambda iteration method for economic dispatch. In the previous lecture, we discussed about economic load dispatch problem, unit commitment problem, and the various case studies that we consider in economic dispatch problem, and what is the necessity of economic operation in power systems. In today's lecture, we'll discuss about the cost function of thermal power plants and its formulation and its importance. And then we'll see about one important technique that can be used in solving economic load dispatch problem, that is Lambda-Iteration method. So first we'll cover about cost function of thermal power plant. So basically, the major generating plants fall into three types: nuclear, hydro, and fossil fuel based power plants. So nuclear power plants are normally operated at constant power output levels. Hydro plants don't have any operating cost because in hydro power plants the input is water, so which is coming at free of cost. Suppose if you take thermal, in thermal the fuel input is coal, so where we have to spend some money. So therefore, the components of cost to be considered in the problem of economic dispatch are the fuel cost of all the fossil fuel plants. So here you can see the figure 1.1 represent simple model of a fossil plant. Maybe you can think this like a thermal power plant, or you can take this as one of the thermal units. So which consists of fuel input that will be given to the boiler, indicated as B here, and then boiler output will be given to the turbine. The turbine output is given to the generator, and then generator will give you electricity output. And that electrical power output you can also use for auxiliary power supply. So the combination of this boiler, turbine and generator all together is called one thermal unit. So in a thermal power plant, you can have so many number of units. So as a part of power system expansion, you can also increase the number of units in the future whenever you need to supply more load demand, that is increased load demand. So from now onwards, so please try to remember, whenever we call unit means it is nothing but the combination of boiler, turbine and generator. So now let's see about the generator operating cost. The total generation cost or operating cost includes fuel cost and the cost that we spend towards labor and also the maintenance cost. So all these costs that we are discussing now is with respect to thermal power plant. It is not with respect to the hydro-based plant, because in a hydro-based power plant there is no fuel cost involved. So that's the reason, as we are considering fuel cost here, so you can think it's the discussion is with respect to the thermal-based power plant. So for the simplicity, fuel cost is the only one considered as variable. So out of fuel cost, labor cost and maintenance cost, most of the cases the labor cost is fixed and the maintenance cost is also fixed. The only variable cost is nothing but our coal cost, because whenever we want to change the power output, we have to supply a variable coal. Either you have to increase the coal input or you have to decrease the coal input, so which will cause the fuel cost variable. The fuel cost is meaningful only in the case of thermal and nuclear stations, but not for hydro stations. As I mentioned just now, in the hydro stations water is the fuel, so which does not require any cost. So that is the reason this fuel cost concept is applicable only in the case of thermal power plant and also nuclear based power plants. So where the energy storage is apparently free in the hydro power plant, the operating cost such as is not meaningful. So the input output curve of a generating unit specifies input energy range. Here you can see the figure 1.2 represent the curve drawn between output power expressed in terms of megawatt and the operating cost or fuel cost. So this operating cost in a simple terms you can express as C of PGI. So basically this cost is a function of power output of each and every unit. So I represent the number of unit. So I may be equal to 1, 2, 3 and so on up to n if there are n number of units. So this operating cost can be expressed in rupees per hour. So for 1 hour of fuel cost, how much money you're spending? So that is called as fuel cost here. Or you can also express this input in terms of input energy rate, because the coal is having a kind of chemical energy. So that energy can be expressed in the form of million kilocalories per hour. So the same thing can also be expressed as M kilocalories per hour, where M represents million kilocalories. So here if you observe, as long as the power output increases, you need to supply more fuel input. So that is the reason the curve is increasing with respect to the power output. So here, if you want to generate the minimum power output, you need to spend some minimum amount of fuel input. And if you want to generate maximum amount of power, you have to supply obviously the maximum amount of fuel input. So this curve drawn between output power versus operating cost or fuel cost is called as fuel cost curve. So it is convenient to express this input output curve in terms of input energy rate, as I told, million kilocalories per hour, rather than fuel cost rupees per hour. Because fuel cost can exchange monthly or daily in comparison with the fuel energy. So the coal cost may vary, but the input energy rate will be fixed. So that's the reason it is so convenient to express in the form of energy rate rather than fuel cost, because the fuel cost depends on market conditions also. So now we'll see one more curve called as heat rate curve. This is called heat rate curve. Here, the input output curve can be obtained from the heat rate curve also. The heat rate can be expressed as F of PGI, Fi of PGI, that is equal to PGI into Hi of PGI, where Hi of PGI is called heat rate and expressed in million kilocalories per megawatt hour. So let the cost of the fuel is K rupees per million kilocalories. Then the input fuel cost function C of PGI can be expressed as K into F of PGI, where F of PGI we can substitute from equation 1.1 here, then it will become K into PGI into HI of PGI. So now this heat rate curve expressed or shown in figure 1.3 can be approximated by using this mathematical equation. So the heat rate curve or heat rate H of PGI can be expressed as AI dash by PGI plus BI dash plus CI dash PGI million kilocalories per megawatt hour, where the coefficients A dash, BA dash and CA dash, all the coefficients are positive. Now by using equation 1.1 and 1.3, you can get the input energy rate function, fuel cost function as F of PGI is equal to AI plus BI PGI plus CA dash PGI square expressed in million kilocalories per hour. Now, the quadratic expression that can be expressed for fuel cost CA of PGI as K into A dash plus K into BA dash PGI plus K into CA dash PGI square. So K is the constant, it is a fuel cost that is constant, and A is also constant, BA is also constant, CA is also constant. So you can modify this equation as AI plus BI PGI plus Ci Pgi square, where Ai is nothing but K into Ai dash and Bi is nothing but K into Bi dash and Ci is nothing but K into Ci dash. So this is the important equation called as fuel cost equation. It is nothing but Ai plus Bi Pgi plus Ci Pgi square and expressed in rupees per hour. So the slope of this fuel cost curve, the slope means you have to differentiate this fuel cost function with respect to the variable power output Pgi. So that fuel cost curve differentiation is nothing but dC by dPg. If you want to express for ith unit, you can express as dCi by dPgi is called incremental fuel cost. In short, you can call this as either IFC or IC, incremental fuel cost, expressed as rupees per megawatt hour, because the numerator is having cost, so you can express the numerator as rupees per hour, and this denominator is having power, so that is nothing but megawatt. So as a whole, this incremental fuel cost can be expressed as rupees per megawatt hour. So this incremental fuel cost equation can be modified as dC by dPgi is equal to, if you differentiate this equation 1.5, the differentiation of this constant Ai will become 0, and then differentiation of Bi into Pgi will give you Bi, plus the third term will become as 2Ci into Pgi, and the unit is rupees per megawatt hour. So now the fuel cost curve and the incremental cost curve may have a number of discontinuities in a real time. The discontinuities occur when the power output has to be extended by using additional boilers, steam condensers, and other equipment. Discontinuities also appear if the cost represents the operation of an entire power station, so that the cost has discontinuities on paralleling of generators. That you can see here in figure 1.3a and 1.3b. In 1.3a, you can see there are discontinuities in the fuel cost curve, because whenever we want to switch on one more unit, we don't have any smooth variation in the fuel cost. Similarly, the incremental fuel cost also will have some sort of discontinuities. So this curve represents practical case. Now let's see about the Lambda-Iteration method that is used for economic load dispatch. So the objective function and constants for the economic load dispatch problem we are going to see now. The economic load dispatch problem deals with optimum allocation of total load demand PD among n number of units. That is nothing but, suppose if there are n number of units and each generator is giving its individual power output, that can be expressed as Pg1 plus Pg2 and so on up to Pgn. That is equal to the total power generation Pg. So where the Pg1 will require its own cost, that can be expressed as C1. The Pg2 will require its own cost, maybe that is of C2, and Pgn will require its own cost, maybe that is of Cn, and the total power generation will require a total cost of generation, that is Ct. So this total cost of generation is basically a function of individual power outputs of each and every generator. So that's why it is expressed as C total is equal to function in terms of Pg1, Pg2 and so on up to Pgn. So now the economic dispatch problem may be treated as a parameter or cost optimization subjected to the satisfaction of constants. And here the system constants are of two types, equality constants and inequality constant. In a simple words, you can remember these system constants as system conditions. So whenever we want to deal economic operation, you have to maintain the system conditions also satisfactory. So now let's discuss about equality constants and then inequality constants. So first coming to the equality constant. So these constants are due to the functional dependencies. That means one function is depending on another function. So mathematically, let's try to understand what is this equality constant. So let f and g have functional dependencies, and the problem is to minimize the function f, where f is a function having variables x1, x2 and x3, and the computed values of x1, x2, x3 are said to be optimal when they minimize both the function f and satisfy the following equality constant, which are described by a set of equations. So let's try to understand these statements. So there are two functions f and g which are having some sort of interlink. So f is a function having variables x1, x2, x3. So now you have to determine the values of x1, x2 and x3 so that for the values of x1 and x2, x3, the function f should be minimum, and also the function g should be satisfied. Nothing but the function g should be equal to 0, where I is equal to 1, 2 and 3 and so on. So this is for x set of equations. So in economic load dispatch problem, the equality constant functional dependency equations are static power flow equations. So basically these are static in nature. So now let's try to adapt this kind of mathematical expression to our economic load dispatch. So in the economic load dispatch problem, you can take the sum of individual power outputs of each and every unit, starting with unit 1, PG1, and then PG2, and so on up to PGN. So the sum of all the individual power outputs of each and every unit can be expressed as summation I is equal to 1 to n, where n is number of units. N is called number of units. That should be equal to power demand. So as a whole, I can say the total power generation should be equal to total power demand. So if you observe carefully here, this is not the real case, because in the real case, the total power generation should also meet the total power transmission losses. So ideally speaking, here once we neglect this total power transmission loss, then you can express as PGI is equal to PD. But practically speaking, in a real power system, our power system is a very big network which is having thousands of kilometers of transmission lines. So definitely all the transmission lines will have some sort of power transmission loss. Then you have to express this equation as PGI is equal to PD plus PL. And this equation is called as power balance equation. This equation is called as power balance equation. So this is about equality constant. So what it means, you are trying to maintain the power equal. So that's why it is called equality constant. So now let's discuss about what are the inequality constants or inequality conditions. The first and foremost inequality constant is each and every generator will have its minimum power rating and also maximum power rating. Once you are using any one generator into operation, it's our duty to ensure that it is generating a minimum amount of power. Otherwise, there is no meaning of using that generator in generating power. At the same time, every generator is having its maximum rated capacity. So it is not advisable to operate any generator beyond its capacity for longer duration of time. If you do so, then what will happen? That particular generator will be overheated because of more current and then more copper losses, then more temperature rise, then ultimately it leads to failure of insulation and damage to the generator. So it's our duty to ensure that each and every generator is giving its power output within the range of minimum limit and maximum limit. It is not only the one unit. Suppose if there are 10 number of units available in one power plant, all the units should be operated within this limit, Pi minimum less than or equal to Pi less than or equal to Pi maximum. This is the first constant. So the first constant is with respect to the active power output. And the second inequality constant is reactive power. So the reactive power generated by individual generating units should be less than the maximum value to avoid rotor overheating and should be more than minimum value to ensure optimal power transfer capability of the system. So always remember that there is a very strong correlation between the reactive power as well as voltage of the system. Suppose if the reactive power is within the limit, then you can say the voltage also can be within the limits. Suppose if the reactive power is not within the limit, you cannot maintain voltage within the limit. So that's why you have to ensure always that the reactive power generation should be equal to the reactive power demand also. Because most of the loads in our power system are of lagging in nature or inductive in nature. So definitely all the inductive loads will require some reactive power. So obviously that reactive power has to be supplied by using the units that are available in the power plants. So the next constant is the total MVA rating of individual units to ensure there is no excess heating produced in the unit. So each and every electrical equipment available in the power system should not operate beyond its maximum kVA or MVA rating, because there is a relation between MVA rating or kVA rating to the temperature rise. If we are operating, let's say, any one transformer beyond its kVA rating, then obviously the temperature rise will increase. So overloading condition of equipment like transformer and lines, you have to ensure that no line in the power system or no transformer in the power system should be overloaded. So they can operate within their maximum limits only. So the next inequality constant is we have to limit the voltage magnitudes and angles to ensure that the system has better stability margins, because there is a relation between the power system stability and the angle. The angle, voltage angle dou, and if you take the power on the y-axis, the curve should be like this. And this you can understand by using this equation. P is equal to EV by X into sine dou, where the power will be maximum when dou is equal to 90 degrees. So always you have to ensure that the power system is operating for a dou less than 90 degrees. So the critical value of dou to have a stability is approximately 30 to 45 degrees. So in nowhere the power system should operate greater than dou is equal to 90 degrees situation. So here the voltage magnitudes also should be limited. Suppose if you are operating any equipment beyond its maximum voltage, then ultimately the dielectric strength of insulation materials will decrease. Then insulation damage will occur. That is what insulation breakdown will occur. So all the systems should operate within the voltage limits only. And the low voltage gives rise to instability and unsatisfactory operation of loads dominated by induction motor type. Suppose if any load is supplied by using low voltage, then the loads cannot operate satisfactorily, because each and every load will require its sufficient voltage for the better operation. So here you have to understand that the voltage should be greater than its minimum value and less than its maximum value. Just like how we are able to maintain active power within the limits, you have to also maintain the voltage also within the limit. And also, as I mentioned, there is a strong correlation between this voltage and also the reactive power. So once you can maintain the reactive power within the limits, then obviously you can maintain the voltage also within the limit. Then high voltage problems shall lead to insulation breakdowns. So as I told, the dielectric strength will reduce if you operate any equipment for high voltage. Then the next inequality constant is transformer tap positions. The tap position should be between the minimum and maximum values. So generally the transformer tappings are provided to have variable voltage output. So you can take whatever the voltage you want between the minimum and maximum values based on the tap position as you require. And the reserve capacities of generating units. To meet the sudden increase of power demand and to maintain good steady state stability of the system, definitely you need to maintain some reserve capacity because you cannot predict the load because the load is very dynamic in nature. So whenever the load increases to very higher value, that means to very peak value, then obviously how to increase the power generation. When the load demand is decreasing, then obviously how to reduce the generation. So in both the ways, you have to balance the power generation along with the power demand. So now let's see the lambda iteration method, that is called as a Lagrange multiplier method. So basically our economic load dispatch problem is a non-linear function. It is not linear in nature. So this non-linear function can be solved by using this mathematical technique called as Lagrange multiplier method. So here you can consider two cases. One is by considering equality constant and the another one is by considering inequality constants also. So our problem is to minimize a function f having variables x1, x2 and so on up to xn by satisfying an equality constant, that is nothing but function gi is equal to 0. So then by using Lagrange multiplier method, we can express as Lagrange multiplier is equal to function f plus summation I is equal to 1 to k lambda I into gi, where this euro symbol is called Lagrange function and lambda is called Lagrange multiplier. So if you observe carefully here, the Lagrange function is having two terms. The first one is the function f and the second one is equality constant. So the necessary condition for minimizing this Lagrange function is differentiate that function with respect to variable and equal to 0. So now this equation 1.25 or 1.26 is representing original constant. And this method is adapted to solve our economic load dispatch, and it can be explained further in detail by taking some numerical problems also in the coming lectures. Now let's see another case, the nonlinear function optimization by considering both equality and also inequality constants. So majority of optimization problems contain both kind of constants, both equality and also inequality constants. Now the problem is minimize the function f by satisfying equality constant, that is nothing but by satisfying function g, and by satisfying inequality constant, that is by satisfying function q. So then you can express the Lagrange function as function f plus the first thing is you have to consider equality constant. So this is nothing but equality and the next term is nothing but inequality. So here the Lagrangian function is having now three terms compared to the previous case. Earlier we have taken up to only second term where we have considered equality constant, but now we have to consider inequality constants also. So that's how now the Lagrange function is having three terms, the function f and then equality constants and then inequality constants. So again The necessary condition to minimize this Lagrange function is differentiate that Lagrange function with respect to variables and equal to 0. Then you will get all these set of mathematical equations. So now this particular equation 1.6 is nothing but original equality constant. And the necessary conditions, whatever we are able to see here, all these conditions are called as Kuhn-Tucker conditions. These are called as Kuhn-Tucker conditions. So we can summarize today's lecture as we have seen the simple model of fossil fuel plant, that is nothing but called as unit. So what is unit here? The combination of boiler and then turbine and then generator. All this set together is called one unit. And then we have seen input output curve of a generating unit where we have taken power output on x-axis and the fuel cost, that is in rupees per hour, in y-axis. Then the curve will become like this. As long as you want to generate more power, you have to increase the fuel cost also. That's why the curve is increasing like this. And then incremental fuel cost. So once you express cost as C is equal to A plus BPG plus CPGI square. So this is called fuel cost curve. I am repeating again. Fuel cost curve C is equal to A plus BPGI plus CPGI square. So this is called cost function. So once you take differentiation of this cost function with respect to power output, then it will give you incremental fuel cost. So this cost can be expressed in rupees per hour. Now the incremental fuel cost, nothing but dC by dP, that is nothing but B plus 2C into PGI. So this can be expressed as rupees per megawatt hour. So this is called incremental fuel cost curve, IFC, or in short you can also indicate as IC. And then we have seen what is the objective function by using different fuel cost functions. And we have seen equality constant, that is nothing but power balance equation. Total power generation PG is equal to power transmission loss plus power demand. And we have seen inequality constants such as voltage constant, active power constant and reactive power constant and transformer tappings. And then we have seen Lagrange multiplier method by considering two cases. One is by considering nonlinear function optimization using equality constant, by considering equality constant, and then nonlinear function optimization by considering both equality and also inequality constants. So we are going to implement all these concepts in the coming lectures in solving some numerical problems, where we will take the help of fuel cost function and also incremental fuel cost function, and also we are going to derive the conditions for economic operation of power system by using this Lagrange multiplier method. So when we are deriving the conditions for economic operation, again we can have two more cases. One is by considering transmission losses, another one is by neglecting transmission losses. So once you neglect the transmission losses, that is nothing but a kind of ideal case. But once you consider the transmission losses, that is a real time practical case. So all these concepts we are going to implement in the coming lectures in solving some numerical problems by using some conditions that are determined by using Lagrange multiplier methods. So that's it for today's lecture. So thank you. We will meet in next lecture.